Here we will take a quick look at principal component analysis, or PCA, and independent component analysis, or ICA, as they're computed in Curry 7. What I'm displaying here are simulated data, and you can see from the map that the activity from the first part of it is from the left side and the second part is from the right side. So now let's take a look at PCA, and what PCA is going to do is decompose this entire interval, which I could change, but I'm using the entire interval, and it's going to decompose it into orthogonal components. So it's going through first and looking for a single component, in which case we can see that we're getting both peaks, but the distribution is not separated into left and right. The second component, and this is based on what's left after the first component has been determined, the second component, or pattern or loading, whichever you want to call it, is now orthogonal to the first but not independent from it. And I went ahead and included the third component even though the signal to noise ratio is very low, just to show you what this looks like and to show you another function of PCA and ICA. Okay, I'm going to add the mean global field power on here at the bottom, and this is just another way of looking at the distribution. Now with PCA, if we wanted to eliminate a single component such as this, we just deselect it and apply the PCA filter, and the effect that it's had is to filter out this loading or this pattern from the range that we've selected. And so you can see that it's basically reduced the noise level. With PCA, if we wanted to filter out just this component, in fact it's going to filter out all of the trailing components that there are, because this third one is based on the second one. The second one is maybe not based on, but computed on the residual from the first one, and so they're not independent. You can't select them independently to remove them. So let's switch over to ICA, and now we see that we've got independent components, and here the first one is showing the left-sided pattern, and the second one is showing the right side, and the third one is again showing noise. And these are independent, so if we wanted to remove just the second one, we can filter it out and you see the results. Red is what the original data look like. The darker blue color is what's left after filtering. Or if we wanted to take out just the first one, we could do that. Or if we wanted to take out just the noise, we could do that. So that's the difference between ICA and PCA. Now let me show you a few real-life examples. Here we have a single epileptic spike, which I will display as a butterfly plot, and I've set the outer cursors to define just this time range. We need to define the interval that we want to use for noise estimation, and I will use a user-defined interval. I'll go from -500 to about, let's say, -50. And now let's do a PCA on these results. And here we see that there are at least 3 components, 3 different patterns, and you can see what the distributions are. I'm going to take the fourth one off and add in mean global field power. And now let me switch over to ICA using the same number of components. And here we see what the first component is. And if we want to take that out, again, we can just filter it out, and we're left with, let me zoom into that. What we're left with is something that has somewhat radically changed what we were looking at. So let me zoom back out. If we take out the second one, again we have quite a change. And if we take out the third one, Now the question here is there any reason that we want to take any of these components out? And the answer is probably not. Let me show you a slightly different way. Here I'm going to expand the range that we're looking at. So now we're looking at the entire time range, but we're still looking at just this spike mainly. And if what we see, if we move to the peak of the second component and see its distribution, we can then move to the peak of the first component, or the second one that occurs in time, and see its distribution. And we can go to the third component and you can see its distribution and time point. What we're looking at is really a moving dipole. This can happen when you analyze the epileptic spikes. What you'll get is a sequence of dipoles and their positions will change across time. And so when you look at the ICA for them, you'll see similar but different components or different patterns. So in this case, there's no reason to try and remove one or two of them. They're all valid components. There's no artifact, and this is what you get sometimes with epileptic spikes. Okay, let me show you another example. Okay, here I want to show you one of the ways of removing blinks from continuous data. There's actually easier ways, but I want to show you this way because you can see the PCA results more clearly. So I'm going to start out by going into template matching, and what I'm going to do is identify all the blinks automatically. So I'm just going to set a time range around the blink and tell it that we're using the VEOG channel. And that looks pretty good. So now I'm going to scan through the file, and this will identify blinks that fit these criteria. And I can see what they are by going to the event list. And it's telling me there are 35 blinks, and we've identified 12 that fit these criteria. So I'm going to change the amplitude criterion to 70%, and now we've picked up most of the blinks. So what I'll do then is change the epoch interval and average the blinks together. And this is what the average looks like. And here we have it in a butterfly plot. And I will change the time range so we're looking at the entire thing. I do want to make sure I have noise estimation computed properly. I'm going to be saving these results, so I need to use a particular type of noise estimation. So now let's take a look at the PCA of the blinks, of the average blinks. And as you can imagine, there is one pattern or one component that is predominating over the rest of them. The SNR is 11. Here it's at 1, and then we get beneath the noise floor. So we really have about 2 components that are probably valid, mainly 1 and possibly 2 or maybe 3 or 4, but the rest of them are going to be rather weak. So let's put the mean global field power on, and we see the distribution looks very much like you'd expect for a blink. So what I'll do now is save these results. I'm just going to call it blinks and overwrite a file I already have. And now let's go back to the continuous data. And I'll go to a place in the file where there are several blinks together. And if we go to artifact reduction, I can take the file that we just created and apply it. As I said a moment ago, there are slightly easier ways we could do a simple PCA or ICA on the continuous data without going through template matching, but I wanted to show you what the PCA display looked like. So I'll go to load file and select the one we just created. And I'm going to change the number of components back to 0. So this is what we get with the blink in place, or with the blinks in place. And now if we want to project out the first component, you can see the blinks have been pretty much reduced. if we want to include the second component, if we want to project it out, the differences are subtle. If you watch up in this area for P3, as I go back down to one component, you'll see that it changed maybe most obviously at that point, but it does change at other points as well. And it looks at this point like we're changing EEG and not blink activity, so I would not use that second component and leave it just at the first one. And so now with the blinks reduced, I would just go on at this point and do whatever the remainder of the analyses were. So that gives you a quick overview of how PCA and ICA are used in Curry 7.